Igneous and metamorphic rocks make up 90 to 95% of the top 16 kilometers of the Earth's crust by volume. Igneous rocks form about 15% of the Earth's current land surface. Most of the Earth's ocean crust is made of igneous rock. Igneous rocks are also geologically important because their minerals and global chemistry give information about the composition of the mantle, from which some igneous rocks are extracted, and the temperature and pressure conditions that allowed this extraction and/or other pre-existing rocks that melted. Their absolute ages can be obtained from various forms of radiometric dating and thus can be compared to adjacent geologic strata, allowing a time sequence of events. Their features are usually characteristic of a specific tectonic environment, allowing tectonic reconstitution. In some special circumstances, they host important mineral deposits or ores. For example, tungsten, tin, and uranium are commonly associated with granites and diorites, whereas ores of chromium and platinum are commonly associated with gabbros. My objective is that by the end of the chapter, from your reading in this PowerPoint lecture, you will be able to distinguish between magma and lava and explain the chemical distinctions among different types of molten rock, describe the special places in the Earth where magmas form, explain why melts move to locations where it solidifies and how solidification takes place, describe and classify different igneous rocks, and discuss where and why igneous activity happens in the context of plate tectonics theory. Remember that igneous rock is formed by the solidification or freezing of molten magma or lava. It seems strange to think of freezing in the context of rock formation. Most people think of freezing as the transformation of water to ice when temperatures drop below 0 degrees centigrade. The freezing of liquid melt to form solid igneous rock represents the same phenomena. Igneous rock freezes at high temperatures between 650 degrees centigrade and 1,100 degrees centigrade. There are two major sources for Earth's internal heat. It is both left over from Earth's formation and from ongoing heat generation. The heat left over from Earth's formation is residual heat that was acquired by the early formation of the planet from accretion, the smashing together and melding of planetary rocky debris, meteors, and planetesimals. The forcing of atoms into ever-decreasing space as we go deeper within the planet generates heat as the atoms and electrons collide. Once temperatures were high enough for iron and other lower melting point minerals to begin to melt, a profound event occurred. This event is known as the iron catastrophe. Once the interior began to partially melt, high-density iron-rich liquids began to sink towards the center of the Earth, while low-density liquids rose towards the surface. In other words, the planet began to differentiate or separate into a densely stratified body. As dense material sank towards the center, more energy was released in the form of heat, causing the temperatures to increase even more, resulting in more melting, more sinking of iron, and more heat being released, a positive feedback process. It is likely that much of the Earth melted in this process. The heat generated by the collision of the smaller planet Theia with Earth generated a portion of Theia was subsumed into our planet. And even after all that, the Earth continued to be bombarded by large meteorites until about 3.9 billion years ago, when the Earth's orbit was cleared of the majority of space debris. Much of this leftover heat from Earth's formation has radiated to space, and the Earth has slowly cooled. However, the Earth has a large amount of radioactive elements and minerals that are decaying that has been sufficient to slow the cooling of the planet overall. The Earth remains very hot. Temperatures at the base of the lithosphere is about 1,300 degrees centigrade, and temperatures at the Earth's center exceeding about 4,700 degrees centigrade. The sun's surface glows at 5,700 degrees centigrade. After the iron catastrophe, the Earth cooled enough for the mantle to solidify, leaving only the outer core liquid. However, partial melting can develop in the upper part of the asthenosphere and in the lower part of the crust. Today, there are three special tectonic settings that melting can occur within the planet. They are 1. Melting due to a decrease in pressure. 2. Melting as a result of the addition of volatiles. And 3. Melting as a result of heat transfer. As we go deeper into the Earth towards the core, the temperature of the rock increases. The rate of change in temperature with depth is called the geothermal gradient. Even though the upper mantle has a very high temperature, higher than the melting temperature of a rock, it does not melt. It stays solid because it is also under great pressure from the weight of the overlying rocks. The atoms cannot break free from the solid mineral crystals. However, if the pressure affecting hot mantle rock decreases while the rock's temperature remains nearly unchanged, the rock may melt from A to B in the diagram. In the image, the black line is the geothermal line, temperature change with increased depth or pressure. The red line is the liquidus, temperature where rock is completely melted at depth, and the green line is the solidus, temperature where rock begins to melt. In the example going from A to B, the rock rises from a solid at higher pressure to a point on the solidus line at lower pressure, but at slightly lower temperatures where the rock begins to melt. Decompression melting takes place where hot mantle rock rises to shallower depths. Examples are 1. Mantle plumes or hot spots. 2. Beneath rifts, such as mid-ocean ridges where the convecting mantle rises. Or 3. Continental rift zones where stretching and thinning of the crust allows the mantle to rise and melting occurs. The packet of rock, surrounded by the dashed line in the images, rises to a zone of lower pressure at a shallower depth, and magma forms, the red dots in the image. In subduction zones, the subducting plate undergoes pressure and heat as it descends. About the time the plate gets to about 150 kilometers deep, water and carbon dioxide that is incorporated in the chemical formula of the minerals in the rock are squeezed out of the rock. It dehydrates the rock, and the dehydrated water forms a super hot steam that supersaturates the asthenospheric mantle above the area. This supersaturated steam lowers the melting temperature of the rock and allows the rock to melt. The magma that is formed, figure on the left, has less density than the surrounding unmelted mantle rock and rises towards the surface. Laboratory studies, figures on the right, indicate that the addition of water lowers the onset of melting of peridotite with depth. The dashed line is the solidus line. The arrow shows that the solidus has moved to a lower temperature curve, forming a new solidus line. The yellow line is the geothermal gradient. For example, at about 90 kilometers depth, the addition of 4% water to peridotite lowers the solidus, the onset of melting, from approximately 1,500 degrees centigrade to approximately 1,100 degrees centigrade. When very hot magma rises up into the crust, it brings substantial amount of heat with it. As we will see later in this lecture, continental crustal rock melts at a lower temperature than mantle rock. The transfer of heat from the hotter mafic mantle rock will melt the felsic crustal rock because the felsic crustal rock has a lower melting temperature than mafic rock. The melted crustal rock is less dense than the surrounding continental rock and will rise to its point of buoyancy and eventually will be distributed on the surface as lavas. As the figure illustrates, this may allow magmas having different chemical compositions to erupt in close proximity or in some cases from the same volcano. Magma is a hot liquid consisting of many chemicals or elements. Geologists tend to describe the chemical composition of molten rocks in terms of the proportion of oxides it contains. An oxide in this context is a molecule consisting of an element bonded to oxygen. Common oxides in magma or lava include silica, SiO2, aluminum oxide, Al2O3, iron oxide, FeO or Fe2O3, calcium oxide, CaO, magnesium oxide, MgO, sodium oxide, Na2O, potassium oxide, K2O. Different melts will yield different types of igneous rocks, depending on the silica content in the magma. Gabbros have about 45% silica content, and granite has up to 76% silica content. Magma contains volatiles. Volatiles are those readily vaporizable materials present in a magma, such as water and carbon dioxide, whose vapor pressures are sufficiently high that they will become concentrated in any gaseous phase that forms. We distinguish between dry melts that contain no volatiles and wet melts which do. Some common volatiles are water vapor, H2O, up to 50% of volatiles in a melt, carbon dioxide, CO2, sulfur dioxide, SO2, nitrogen, N2, and hydrogen, H2. Because magmas and lavas release volatiles that make up rocks from the Earth's interior, they also release volatiles that comprise our planet's water and air. There are four major compositional types of molten rock depending on the overall proportion of silica relative to the combination of magnesium oxide and iron oxide that a melt contains. For example, mafic rocks contain a relatively high proportion of magnesium oxide and iron oxide relative to silica. Ultramafic means an even higher proportion of magnesium oxide and iron oxide to silica. Felsic magmas have a relatively high proportion of silica relative to magnesium oxide and iron oxide. Intermediate magmas fall between mafic and felsic melts. The percentage are based on the weight of silica per volume of rock. Molten rocks vary in composition due to the following factors: source rock composition, partial melting, assimilation, and magma mixing. We will look at each factor in the next 4 slides. The source rock composition represents the composition of the melt. If the initial melted rock was derived directly from the mantle, then the magma will be either ultramafic or mafic. If the initial melted rock was derived from either marine crust or continental crust, then the magma may be either mafic, intermediate, or felsic. Partial melting. Only 2 to 30% of source rock melt to produce magma. Magmas formed by partial melting are more felsic than the source rock from which they are derived, because the silica minerals melt at lower temperatures, and more silica enters the rock than remains behind in the still solid source rock. Number 3, assimilation. Changes a melt's composition due to incorporating chemicals dissolved from the wall rock of the magma chamber or from rocks breaking from the chamber wall called xenoliths and sinking into the magma. This process is known as stoping. Sometimes unmelted xenoliths are found in solidified magma chambers that are exposed on the surface. And a xenolith figure on the right can often give geologists clues to the country rock the chamber formed in long after the country rock has been eroded away. In this image, the xenolith is probably a quartzite or metamorphosed sandstone, suggesting that the original rock the magma invaded was a sandstone, a sedimentary rock. Number 4, magma mixing. Different magmas from different source rock may enter the same magma chamber. Mixing a felsic magma with a mafic magma in equal proportions produces an intermediate magma. Not all magmas mix thoroughly, as shown in the thermal image on the left. When this occurs and we have rapid solidification by extrusion, we can get igneous rocks that have two different types of igneous rocks contained within the outcrop, as shown in the image on the right. The light-colored igneous rock is rhyolite, a felsic rock, and the dark igneous rock is basalt, a mafic rock. Magmas rise for two reasons. First, because magma is less dense than the surrounding rock, like a bubble in water, and rises due to a buoyancy force acting on it. It wants to rise until the magma density matches the rock surrounding it. Secondly, the weight of the overburden produces pressure at depth, and this pressure squeezes the magma upward through cracks in the rock. The same thing occurs when you step in a mud puddle while barefoot. Your weight squeezes the mud up between your toes. The speed of magma flow is governed by viscosity. Viscosity is the resistance to flow. For example, syrup has a greater viscosity than water, or cold honey has a greater viscosity than warm honey. The viscosity of magmas or lavas depends on temperature, volatile content, which is the amount of gases in the melt, and silica content. Mafic lavas have a low viscosity when compared to felsic lavas. Mafic lavas can travel for hundreds of kilometers, whereas felsic lavas generally travel less than a kilometer or two. Mafic basalts or lavas have a higher melting temperature. They contain less volatiles and less silica content than do felsic magmas or lavas. Mafic lavas flow easily and are less viscous than felsic magmas or lavas, which are stiff and are considerably more viscous than mafic lavas. The cooling rate of magma depends on three factors: the depth of the intrusion, the shape and size of the magma body, and the presence of circulating groundwater. Cooling happens when magma rises towards the Earth's surface because the geothermal gradient decreases as we get closer to the surface. A small body of magma cools more rapidly than a large body. A body of magma with the shape of a pancake cools more rapidly than one with the shape of a melon. Magmas that interact with circulating groundwater cools more rapidly than magma that intrudes dry rock because circulating groundwater removes heat. Mafic minerals solidify at a higher temperature than felsic minerals in a melt. As a result, the iron, magnesium, and calcium are removed as early mafic minerals settle to the bottom of the melt. As a result of this process, the remaining magma melt becomes enriched in silica, aluminum, sodium, and potassium elements that will evolve into felsic minerals as the melt progressively cools. This is called fractional crystallization. In essence, fractional crystallization is the removal of early formed crystals from an originally homogeneous magma, for example by gravity settling, so that these crystals are prevented from further reaction with the residual melt. Fractional crystallization was modeled after a series of experiments conducted by N.L. Bowen that he derived from heating and cooling melts. He discovered, as we mentioned on the last slide, that iron, magnesium, and calcium are removed as early mafic minerals settle to the bottom of the melt. As a result of this process, the remaining magma melt becomes enriched in silica, aluminum, sodium, and potassium elements that will evolve into felsic minerals as the melt progressively cools. He discovered that minerals solidify in two specific series, a continuous series and a discontinuous series. In the continuous series, calcium-rich plagic clays feldspar begins to solidify around 1,457 degrees centigrade, and sodium-rich feldspar ends its continuous series at around 890 degrees centigrade. The other series is discontinuous. Minerals start and stop crystallizing, beginning with olivine around 1,540 degrees centigrade, then pyroxene, amphibole, biotite mica, potassium feldspar, muscovite mica, and finally quartz at around 700 degrees centigrade. He also determined mineral composition and temperature ranges for the four classes of igneous rocks. We will discuss mineral composition later in this lecture. You should know both the continuous and discontinuous igneous mineral series. Some volcanoes erupt streams of lava that cover broad swaths of land with relatively thin lava flows, like the image on the left. These are low viscosity basalt flows. Others erupt highly viscous masses of felsic lava that pile into mounds of angular blocks, like the image on the right. Still other volcanoes erupt lavas in a cataclysmic explosion, which forcefully ejects turbulent clouds of pyroclastic debris that can rise tens of kilometers into the sky, like the image on the left. These lavas have an abundance of volatiles that shatter and disperse the lava into lapilli, pita golf ball-sized fragments, the middle image, that fall like hail on or near the volcano. The expanding gases may break the particles into finer dust-sized material known as ash, image on the right, which may be carried by the wind for great distances before it drifts down from the sky like snow and accumulates in layers. Magma rises and intrudes into pre-existing bedrock by slowly percolating upward between grains or by forcing open cracks or fractures in the country rock. These are called tabular intrusions. They are roughly planar, with a uniform thickness that varies from a few centimeters to hundreds of meters thick. There are two types of planar intrusions: a dike that cuts vertically or diagonally across pre-existing layers of rock, and seals that are injected parallel to the rock layers. This slide shows examples of dikes. The upper photo and illustration are vertical dikes that are radiating away from a volcanic neck or vent. In the lower photograph, we see a diagonal dike cutting across pre-existing sedimentary rock. This is a great example of a seal, a horizontal, tabular, intrusive igneous body that intrudes and parallels existing strata. In some places, the magma injecting between layers gets blocked and can't spread laterally very far, so the magma accumulates to form a blister-shaped intrusion known as a laccolith, L-A-C-C-O-L-I-T-H, that pushes the overlying strata upward into a dome. In the photograph at the lower left, pink monzonite laccolith intrudes within the gray Cambrian and Ordovician strata near Notch Peak, Utah. Monzonite is an igneous rock that straddles the intermediate to felsic class boundary. Plutons are irregular or blob-shaped intrusions or magma chambers that range in size from tens of meters across to tens of kilometers across. Intrusions of numerous plutons in a region yields a vast composite igneous body called a batholith, B-A-T-H-O-L-I-T-H. that may be several hundred kilometers long and over 100 kilometers wide. The lower left photograph is a view of the exposed batholith in Yosemite Valley within the Sierra Nevada range. If intrusive igneous rocks form deep beneath the Earth's surface, why can we see them exposed today? Over long periods of geologic time, mountain building slowly uplifts belts of crust. Erosion by water, wind, and ice can gradually strip away the thick overlaying rock and expose the intrusive rock plutons formed below. Some of the plutons exposed in mountain cliffs today solidified kilometers to tens of kilometers below the surface, as the example in the photograph on the left. How do we describe igneous rocks? Color generally reflects a rock's composition, but color is influenced by grain size and by the trace amounts of impurities. In general, a rock's color grades from very dark ultramafic rocks to very light felsic rocks. Geologists commonly refer to an igneous rock's texture to be crystalline, fragmental, or glassy. Crystalline igneous rocks consist of mineral crystals that intergrow when the melt solidifies so that they fit together like a jigsaw puzzle. Different crystals grow at different rates and at different times. As the crystals grow, they interfere with each other. We distinguish subcategories of crystalline igneous rock by the size of the crystal. Very coarse-grained rocks with crystals large enough to see with the naked eye are identified as phaneritic, P-H-A-N-E-R-I-T-I-C. They reflect their intrusive environments by cooling slow enough to give the crystals time to grow. Very fine-grained crystalline structure that one cannot see the individual grains with the eye are termed aphanitic, A-P-H-A-N-I-T-I-C, aphanitic. Extrusive aphanitic rocks cool rapidly, and the crystals do not have time to grow. They are microcrystalline. The final texture class is porphyritic, P-O-R-P-H-Y-R-I-T-I-C. Porphyritic rocks that have large crystals called phenocrysts are surrounded by a mass of aphanitic crystals called a ground mass. Porphyritic rocks indicate that the rocks spent part of its formative period as an intrusive rock that was interrupted and expelled or extruded rapidly onto the surface, causing the rest of the crystals to quench rapidly, forming the ground mass. Fragmental igneous rocks form from pyroclastic debris and consist of igneous chunks, grains, or flakes of broken volcanic rock that are packed together or welded together or cemented together by the surrounding volcanic ash. Geologists distinguish different types of fragmental igneous rocks from one another by fragment size. Fine-grained to medium-grained rock fragments in the pyroclastic rock on the left, and medium to large-grained rock fragments in the pyroclastic rock on the right. Rocks made of a solid mass of glass or of glass surrounding isolated small crystals are glassy igneous rocks. Glassy rocks tend to fracture conchoidally. These rocks must cool extremely fast, for example, in water. The extremely rapid cooling does not allow the minerals to crystallize. This is an obsidian rock. Note the conchoidal fracturing of the rock, especially in the area below and to the right of the penny. We classify crystalline igneous rocks into four compositional groups: ultramafic, mafic, intermediate, and felsic. The chart shows that the freezing temperatures decrease Density decreases and silica content increases from ultramafic to felsic compositional groups. In the middle, we see texture and a rock name for each compositional group. The third or right column shows the mineral composition by percent. Rhyolite is the aphanitic felsic rock, and granite is the phaneritic felsic rock. They both contain the minerals sodium plagioclase and potassium feldspar, amphiboles, biotite mica, and the mineral quartz. Andesite is the aphanitic intermediate rock, and diorite is the phaneritic intermediate rock. They both contain the minerals pyroxene, sodium calcic plagioclase feldspar, amphiboles, biotite mica, and quartz. Basalt is the aphanitic mafic rock, and gabbro is the phaneritic mafic rock. They both contain the following minerals: olivine, pyroxene, calcic plagioclase feldspar, and amphiboles. Komatiite is the aphanitic ultramafic rock, and peridotite is the phaneritic ultramafic rock. They both contain olivine and pyroxene. Ultramafic rocks are extremely rare on the surface of the Earth. Peridotite is found only in the mantle, and only special tectonic forces bring it to the surface. Komateites are rare and predominantly found in rocks of Archean age. This restriction in age is thought to be due to cooling of the mantle, which may have been 100 to 250 degrees centigrade hotter during the Archean, which is 4.0 to 2.5 billion years ago. The early Earth had much higher heat production due to the residual heat from planetary accretion, as well as the greater abundance of radioactive elements. Lower temperature mantle melts, such as basalt and pickrite, have essentially replaced komateites as an eruptive lava on the Earth's surface. The color of an igneous rock provides a rough guide to its composition. Mafic rocks tend to be black or dark gray, intermediate rocks tend to be lighter gray or greenish gray, and felsic rock tends to be tan to pink or maroon. The most common glassy textured igneous rocks are obsidian, pumice, and scoria. Obsidian is a vesicle-free felsic glass that tends to be black or brown in color and exhibits conchoidal fracturing. Pumice is a felsic rock with about 75% to 90% vesicles. Vesicles are open holes in igneous rock formed by the preservation of bubbles in magma as the magma cools to solid rock. The rock forms by quickly cooling of frothy lava. The froth develops when lots of gas bubbles come out of solution but can't escape due to the high viscosity of the felsic magma. Pumice, the image on the left, floats in water. Scoria is a mafic volcanic rock that contains about 30% vesicles. Scoria has larger vesicles, contains more glass between vesicles, and is denser than pumice. There are three different types of tephra or pyroclastic materials ejected from volcanoes. They are ash, that is less than 2 millimeters in diameter, lapilli, felsic, and cinders, mafic, are 2 millimeters to 64 millimeters in diameter, and blocks or bombs that are larger than 64 millimeters in diameter. There are three kinds of volcanic pyroclasts: tuffs, volcanic breccia, and volcanic agglomerate. Tuff on the left is a fine-grained pyroclastic rock composed of volcanic ash or ash mixed with lapilli composed of pumice. Volcanic breccia in the middle consists of angular fragments of pyroclastic debris that have been cemented together. Volcanic agglomerate, right, consists of accumulations of lapilli or bombs, and the larger class are rounded. Most igneous activity occurs along volcanic arcs of convergent boundaries, along the mid-ocean ridge axis of divergent boundaries, or within continental rifts where the continents undergo stretching, and at isolated hotspots that occur on both marine and continental plates. Clearly, plate tectonics govern the process that lead to melt production within the Earth. Most subaerial or marine volcanoes on Earth reside in volcanic arcs at subduction zones. The subducting plate undergoes pressure and heat as it descends. About the time the plate gets to about 150 kilometers deep, water and carbon dioxide that is incorporated in the chemical formula of the minerals in the rock are squeezed out of the rock. It dehydrates the rock, and the dehydrated water forms a superhot steam that supersaturates the asthenospheric mantle above the area. This supersaturated steam lowers the melting temperature of the rock and allows the rock to melt. The magma that is formed, figure on the left, has less density than the surrounding unmelted mantle and rises towards the surface. A volcanic arc parallels the arcing subduction zone about 150 to 300 kilometers from the axis of the trench up on the non-subducting plate. If they occur on continental plates, they are called continental arcs. Examples are the Cascades and Andes Mountains. If the non-subducting plate is marine, it is called a volcanic island arc, such as the Aleutian Arc of Alaska and the Mariana Arc of the Western Pacific. Not all the basalt magma rises to the surface. Some gets trapped at the base of the continental crust and some in the marine crust. When this occurs, fractional crystallization and/or assimilation happens and produces felsic or intermediate lavas. Most of the igneous activity at the Earth's surface occurs at mid-ocean ridges. The entire marine crust, a 7 to 10 kilometer thick layer of basalt and gabbro that covers about 70% of the Earth's surface, forms at mid-ocean ridges, and almost the entire volume gets subducted and replaced by new crust every 200 million years. Magmas form at mid-ocean ridges due to decompressional melting. Along the edges of the magma chamber, the magma cools and forms gabbro. The rest either infiltrates fractures within the marine crust and forms basalt dikes, or is booshed out on the ocean floor and forms pillar lavas. Pillar lavas are mafic lavas that extrude underwater to form blob-like shapes or pillars that typically have glassy rinds from cooling very quickly. Rifts occur at places where continental lithosphere undergoes horizontal stretching and vertical thinning. As the process takes place, pressure on the asthenosphere decreases and decompressional melting occurs, producing basaltic magma. Part of the magma gets trapped below or in the crust and forms felsic magmas that erupt as ash. As a result, extrusive rocks in a rift are bimodal and include both basalt flows and sheets of rhyolitic tuff. According to the plume hypothesis, the plume rises from the lower mantle near the core as a column of hot, plastic, solid rock that rises a few centimeters per year. When the plume rises to the base of the lithosphere, decompression causes partial melting, producing mafic magmas. Some undergo fractionalization and produce a felsic magma. The escaping magmas produce isolated volcanic mountains rising from the ocean floor. As the ocean floor moves, the volcanoes go extinct and new volcanoes form, creating over time a chain of volcanoes. An example is the Hawaiian island chain of volcanic islands on the Pacific Marine Plate, or Yellowstone on the North American continental plate. A large igneous province, or lip, L-I-P, is a region in which large volumes of lava and/or ash erupted over a relatively short interval of time. These are low viscosity mafic basalt that flow for tens to hundreds of kilometers. These are termed flood basalts. The largest of these is the Ontong Java Oceanic Plateau of the Western Pacific that covers an area of 5 billion square kilometers on the seafloor and has a volume of 50 million cubic kilometers of basalt. Flood basalts make up the bedrock of the Columbia Plateau in Oregon and Washington and the Deccan Traps of India. They are thought to be super plumes in the mantle, plumes that bring up vastly more hot asthenosphere than ordinary or normal plumes like the Hawaiian plume or hotspot.